Today we are assembled here for the discussion of synthesis. Hope you know what is meant by synthesis. Before synthesis team, uh, see, I want to tell you what are the different areas, various like areas in physical design domain, PD. See, in physical design, whenever the code gets ready, which is front end, until that whatever the RTL code is independent of the technology. Yes, of course, before starting of the design, the technology, fab house, everything will be decided. But coming to the codes, whatever, it is independent of the technology. From synthesis onwards, the right like whatever the technology will be counting. Remember it. This is one of the important thing. Yeah, fine. Yes, team, synthesis. So in PD physical design domain, synthesis is the beginning, it is the first stage. Afterwards, we have place and route. In place and route itself, some of the engineers works for only power analysis. Some of the engineers works for DFT. Some of the PD engineers may work on physical verification, and some of the engineers work on STA, static timing analysis, and all these are the various areas in PD. So I could say in physical design domain, synthesis is the first stage. In backend, what I mean is in backend. Now let us get started. Synthesis. What is meant by synthesis? It is simply, guys, we are converting that RTL code, whatever, into optimized gate level netlist. Yes, optimization in the sense in terms of timing, area, and power. And in these three areas, the main the main important parameter to us is timing. So I can say it is a conversion of RTL to gate level optimized gate level netlist by meeting timing, area, and power mainly on timing. So till now, before that, whatever the syntax or the logic gates or whatever, now we want the, if you want to go for place and route, you want the gate level netlist that will be generated by none other than synthesis team people. Now, coming to the synthesis, which tool we use? So coming to the cadence environment, we use cadence genus. If it is synopsis environment, we use design compiler DC. Now, let's have a just before going to discuss about design flow, we will have some what are the strategies. Suppose if there is a design, in two ways, the people can do synthesis. In one way, they can take the entire design as a single entity. They'll design, they'll run, and they'll go at one length. Whereas in bottom-up approach, in hierarchical approach, they divide the entire design into uh, different modules. By modules wise, they do the synthesis, and finally they integrate in the top level. So here, coming to the top-down approach, if there any advantage means yes, because everything is under control of one particular person, so you can get a well-optimized design. However, it requires huge runtime, and you require servers according to that much, whatever the complexity of the design. And as you are taking the entire design as a single entity, you require more memory as well. And to that memory, that huge memory that you want to run, so you require high-end servers, and multiple servers won't work. That's the reason, definitely the top-down approach, whatever the approach, is going to be delayed. Whereas in bottom-up approach, of course, when compared with top-down approach, there is less optimization. However, there are more advantages that you can see. For better understanding, I have given a green color. It requires less runtime, less memory, low-end servers, multiple persons can work, so that the design may not get delayed, and it may get ready. It may get ready on time. So here, if you ask me, sir, for if there is a Vaishnav, if there is a design, like whether can I go for top-down approach or bottom-up approach? If your design is so complex, then go for bottom-up approach or hierarchical design. If the design is a little complex, then you can go for top-down approach as well. That's what. But most of the engineers, as the design is becoming more and more and more complex. So here, uh, most of the engineers, most of the people select bottom-up approach only, because here we divide and conquer. That's why it is also called as divide and conquer approach, like that. These are the two strategies which are present in synthesis. Now, let us take a logic synthesis in a broader view. What are the logic synthesis? What does it require? It requires RTL code, register transfer level code. It is either HDL code or like HDL code. It could be like a Verilog or VHDL. Of course, most of the people in industry uses
Hello, sir.
Verilog. Yes, yes, yeah. Any concern?
Sir, I have a question, sir.
Yeah, yeah. Please.
Sir, I'm
Just write in the
beginning.
chat box. Write in the chat box. I will remove you. I will remove you. Write in the chat box.
Can I continue, Rajat?
I just continue. If you unmute again, I will remove you without any warning. Yeah, you can continue. You can write in the chat box.
Okay. So coming to the logic synthesis, the inputs required, that is RTL code, and we want SDC file which contains the clock information, and timing libraries .lib files which contains the cell delay information and even power information, leakage current information, and physical libraries. Of course, in like actually there are two types of synthesis. One is logic synthesis, another one physical synthesis. The synthesis engineer, like who is appointed as a synthesis engineer, as an entry level, you are allowed to work on logic synthesis only. If you are having more than 2 to 3 years of experience, then only you are allowed to go for to do physical synthesis. So if it is physical synthesis, then you require physical libraries, in the sense whatever that particular cell minimum width, minimum height, are the all those, I mean, in a single word I can say geometry information. .lib file contains timing information, and the physical libraries contains that geometry information. And if your synthesis is included in with DFT, then you require, yes, scan config file. If you are working on different power intent multi VDD, then you require UPF file. If there is a simple logic synthesis, then RTL code, SDC file, .lib files are enough. These three are the mandatory inputs required for the logic synthesis. And what are the outputs? As I said, logic synthesis converts the code into optimized gate level netlist. So that is, you can see here, gate level netlist.vg file. See, this RTL code, RTL code will be in .v file, and this is .vg file, and this is a .sdc file. You can ask me, sir, what is the difference between the design constant, this SDC file and this SDC file? Are they different? See, team, what I mean is, initially, I get the clock information, the related, all the information which is provided in the SDC. During the logic synthesis, if I add anything related to the clock, then that will be updated in this output SDC file. Sir, nothing is updated, sir. As it is input file only. Then, in such case, input SDC file and input SDC file and output SDC file are same only. So here we are saying that if at all, if is there any modification, that will be loaded in output.sdc file. Now, team, after logic synthesis, see, you are converting the RTL code into gate level netlist. At the end, functionality should not change. Whatever you want to do, you can do. but at the end functionality should not change, right? Whether functionally they are same or not, you want to check. That we do here, like with the .do file. That is an input for LEC logical equivalence check. And this logical equivalence check, what it do is it checks the functionality, whether functionally they are correct or not. And if you are including the DFT in your logic synthesis, then this scan config file related the output file, here you get the scan def. This is what team, like orally, what are the inputs and what are the outputs, the overview of logic synthesis. Now, as I said, there are two types of synthesis, logic synthesis and physical synthesis. Let's see here. Types of synthesis, there are two, logic and physical. And here you can see in physical synthesis, along with the inputs required in logic synthesis, here we require one more file, which is a floor plan def file. Floor plan def file contains the location of the cells information. Yes. So here we take this floor plan def file and we do the synthesis. If you consider that floor plan def as well, then it comes under physical synthesis. And for better timing and optimization, people considers physical synthesis only. But remember team, as of my knowledge, I'm telling you, if you are more than 2 to 3 years of experience as a synthesis engineer, then only you are allowed to go with the physical synthesis. But remember. And now, without any delay, let us start the synthesis design flow. This is our actual agenda. This is whatever I have collected and I have given to you is just for the introduction and awareness purpose. That's it. Now, guys, in every interview, people will ask you what are the goals, what are the input files, what are the output files. Similarly, here as well, what is your goal in synthesis means I want to optimize a gate level netlist. That's it. And yes, we want to insert the scan chain if the DFT is included within the synthesis, within the particular synthesis, then we need to insert the scan chain. And to get the low power design, we need to insert the clock gates. And you need to do the optimization. Simply, it is not converting. Remember, team, it is not conversion of gate like RTL code to gate level netlist, optimized gate level netlist. And we will discuss what are the optimization techniques as well. And finally, logical equivalence check between the RTL code and the netlist. RTL is the source code and netlist is the synthesis output. And you need to check whether functionally they are correct or not. So these are the goals in a synthesis, like goals of synthesis. Now, yes, team, this is our synthesis design flow. What is the first step? We need to load the libraries, because here, whatever the the source code contains, like for example, if it is a half adder, sum is equals to A XOR B, you write just A XOR B only, whatever the syntax. But now to that particular XOR, whether particular, as I said, synthesis, from synthesis onwards, the technology, whatever, it is technology dependent. Coming to as per the particular technology, what are the allowed particular cells available, what and their drive strengths, etc. So for corresponding for those cells, corresponding lib files we want. So here in loading libraries, first of all, lib files. If you are doing physical synthesis, then you require left files. And clock information is must and should. That's a design constraints. We want .sdc file. And here in loading libraries, as of now, first we are taking just .lib files and left files. If it is physical synthesis, then without any delay, we go for design attributes. Team, design attributes in the sense, suppose you have written the whatever the code is there, and you are going to source it by invoking the tool and you sourced it. Then it shows some error, like a report. Do you want the detailed report or you want the cut short report? Here, there is one command, some information level from 0 to 9. If you choose 2, then the report will be in a cut short and sweet. Do you want the detailed report then you can go for 9 as well. In 9, you'll get the detailed report. Most of the people, most of the cases, we consider 6 to 7. And if you don't inform to the tool, then also by default, tool will assume some of the things. So if you sir, I have not at all informed to the tool, but still the tool is very matured team. Remember, if you don't tell also, it understand. Okay, no problem. I understood your concern. I'll assume whatever the assumptions are required. Like that, the tools are very matured. Remember. So there's design attributes that we will see. Even I'll show you team design attributes. What are the different commands that we use and all. Now it's time to import the RTL code. Either it is a Verilog or VHDL. We use Verilog only. It is also called as HDL code, hardware description language code. Once you import the RTL code, we do analyzation and elaboration. In elaboration, what we do in the sense, in elaboration, we will check that quality of the RTL code. Like, hello, yeah. Is there any unresolved references? Is there any empty modules, block boxes? It checks the quality of the RTL code. That's it. They have done right in front end. Why again are you do? Why again you are doing? Yes, it's my design, right? It's my duty. It's my job. So I'm checking what's wrong in that. So you need to do team. Remember, elaboration is must and should. It is one of the important step. Once that is done, you have done the quality checking on RTL code. Till now, the .sdc is not at all introduced. Once elaboration is done, we import .sdc file, which is absolutely related to the clock information. Once you imported the SDC file, then you need to check the quality of the .sdc file as well. Definitely, for that reason, we are doing sanity checks. Coming to the sanity checks, what is meant by like sanity checks? Here, sanity checks are checking the quality of the design, quality yes, in a single word, quality of the design. And there are two commands like check design and check timing. The same commands are applicable to Cadence environment and even in Synopsys design compiler as well. Same check underscore design, check underscore timing. And the main thing till now we said you are converting from RTL code to synthesis, right? That's the main thing that here it's going to perform here, synthesis. This one that we will see one by one, whatever the synthesis it contains 3 stages that we will see. And usually team in synthesis, there are 2 ways. We do till synthesis and then we give the same the design whatever to the DFT team. They insert the scan chains and they do incremental optimization, and they'll give to the synthesis team. And then again here we take we move forward. In some cases, synthesis team only do this DFT. Yes, so I can say it is an optional. So once it is done, see, after synthesis it is converted. That's it. So we need to go through the outputs, which contains which are output gate level netlist .sdc .do file and all, and you need to see the reports and all, and sign off checks. What are sign off checks? After synthesis, we need to check whether functionally okay, optimization is done. During the optimization, do we violate any functionality issues? We need to check. That will be done by LEC. At the same time, we need to check the timing, whether it timing closer there or not. So STA. So this is orally the design flow of a synthesis team. Now let us see. Yeah, this is in a detailed manner, loading libraries and design attributes. Yeah, please please mute yourself. Okay, design attributes. C team. Here, if there are constant 0 flops and constant 1 flops in the design, that that the output will be always 0 and 1 only, right? So those whatever the constant 0 flop and 1 flop, unused register, unintentional latches must not be there in the what we call in the design. So for that reason, what we do is we take the command. See here, set underscore attribute LP insert clock gating for the clock gating thing, and here on latch true. So that if you take set attribute HDL error on latch true, if there are any latches, the tool will ignore. And if there are any black boxes, true means it will ignore. And even you can take the information level from like as I said from 0 to 7, 0 to 9, you can take 7 like that. Team, I don't know whether it is correct time or not, but I want to add, that's it. Mostly we don't use latches. We don't use unintentional latches. Intentionally you want to use, then you can use. We use in clock gating only. But we avoid mostly the latches because the latches input is always a combination circuit. In combination circuit output, there will be glitches that you can't avoid them. But this particular latch allow the same glitch to the output of the latch as well. But whereas if you take flip-flop, the glitches will be fixed by the flip-flops. That is the reason we prefer only flip-flops, not latches. So again, I'm briefing you. We don't use unintentional latches. Got it? Now, see here, import RTL code, analysis and elaborate. It read all the HDL files and it checks whether any syntax errors are not. And team, uh, elaborate, we call it as we like the whatever the process elaborate. We call this we call it as a elaborate in cadence, but in synopsis it is linking. The people use linking word because for a design, you don't get only one RTL code. There will be multiple RTL files, and you need to link them to get a complete design structure, complete design information. Hence, in synopsis, people use linking. So don't get confused. Elaborate linking, both are same. It depends on the environment, the people who are using. Now, guys, here in this during elaborate, whatever I said here, you can see clearly the tool checks whether it contains unresolved references, black boxes, empty modules, and all. Here and even if any dead code dead code removal is possibility, are there any switches are there that you can remove? All these things means it is checking the quality of the particular RTL code. That's it. That's it. Now, once that is done, we go for sanity checks. In sanity checks team, if I type check underscore design hyphen all, then it takes all the takes the entire design and it checks in terms of design aspect, whether it contains combinational loops or not, whether it contains any tri-state buffers and latches and any floating inputs. It will trace. If it finds any kind of things which are mentioned here, those will be informed to the informed in console, like in command window. It will trace out, that's it. So he's going to fix it, no, it will trace and it will let you know, that's it. Okay, hope you know why the design must not contain tri-state buffers, because of bus contention issues. So because of bus contention issue problem, we don't prefer tri-state buffer. And as I said, latches we don't use. And even multi-driven inputs and outputs, floating inputs and outputs, guys, multi-driven output, whatever the multi-driven output nets causes power disasters condition. Means there will be a path, low impedance path from VDD to the ground in multi-driven output nets, which leads to damage of the IC. That concept is called power disasters condition. Hence, remember, in a design, there must not be multi-driven output net because it is going to damage the IC. Even similarly, floating inputs as well, because if the input is floating from the outside environment maybe because of the noise, it attains some value in such a way that uh, let us assume a CMOS inverter where both CMOS and NMOS are going to switch on. Hope you know when Vin is equals to VDD by 2, both the MOSFETs, PMOS and NMOS becomes enters into saturation region. So if it attains a particular value where PMOS and NMOS are going to on, there will be impedance path, low impedance path, which causes damage of the IC. Hence, there must not be floating inputs as well. Of course, multi-driven input nets must not be there. Floating outputs must not be there. Yes, however, multi-driven input nets and floating outputs are not the source of our disaster condition. So like few more are there team. Similarly, check timing. This is about design and this is about the timing, like whether you need to check whether clock is reacting to each and every clock pin of the flops. Sorry team, it's my mistake here during a hurry. Here I have written o must be there. I'll correct it later. Okay, I'll update the same. And whether multiple clocks are arriving the same flop or not, that must not be there, right? So related to the clock, do you want to check? Then we go for check timing. Yes, team. These are the sanity checks, which are very important and mm, frequently asked interview question that I can say. Yes. Now, synthesis. It is a picture perfect example team. I have taken this from VLSI Backend Adventure. I'm grateful to them. Yeah. Now, take this in synthesis. This is the main synthesis stage team. Whatever till now we have we have been telling, we are converting from RTL code to optimized gate level netlist. Where are you doing? Till now you are taking that, this, you are checking the design, you are checking the timing. Now we are doing the conversion. It includes three stages. One is syn generic, syn map, and syn optimization. In the figure you can see here, you can see here, it's a code, Verilog code, HDL sources. This is the code. First of all, you need to convert this code. Till now you have written some, maybe it may require some mux or XOR gate or NAND gate or whatever. And this code must be converted into the some logic gates, right? First, you need to convert into generic cells. Remember, directly you're not at all going to map with respect to the technology. First, from the library, we use generic cells. What is meant by generic cell? It doesn't have any drive strength, any certain specification, just like generic. Once the design, like whatever this, you can see that blue color, the middle one. Now the code becomes the diagram, including the logic gates, gate level. Yes. Now this one is there. Once you convert it into generic logic cells, now according to our technology, we do technology mapping, mapped to given technology. Okay, are you doing 45 nanometer, 28 nanometer? In 28 nanometer, coming to the AND gate, how many AND gates are available? How many adders are available? What are their drive strengths? All these information that uh, hello. Okay. Uh, that will be technology, like that will be done in the mapping team. That is called a syn mapping, mapped to given technology. Once it is mapped, now optimization. This is syn opt. So guys, I can say from this command, whatever the syn opt, I am confidently proving my definition, saying that it is the process of converting the RTL code into optimized gate level netlist. Why I'm using optimized? Because I am doing here optimization. See here, just I'm explaining from the figure. Here you can see 1, 2, 3, 4, 5, 6. 6 gates are there, but here some 4 gates are there. Just I'm not bluffing you. Just I'm telling you the, like, just explaining the figure. So in optimization, in terms of timing, in terms of area, in terms of power, it's going to like uh, what we call optimize. This is called syn optimize. If something says what is synthesis, it includes three stages: syn generic, syn mapping, and syn optimization. So if you understand this figure, you understood about synthesis. That we can say. Now team, once the synthesis is done, then yes, then you can say this yeah, DFT, and then reports and outputs of sanity checks only. So there is nothing more, main the synthesis. So before that, I want to give a few more details regarding the optimization techniques, which are some, it's a good to go concepts. Okay, now optimization we can do in three aspects. That is delay, in terms of delay, in terms of area, in terms of power. Coming to uh, okay, uh, just a second team. What is drive strength? Team, here coming to the drive strength, for example, let's assume a CMOS inverter. To make rise time and fall time are equal, means that the time periods are equal, we take the PMOS width as 2W and NMOS width is W. If it is so, is my voice audible team? Hello? Hello?
Audible, sir. Audible. Audible.
Okay, okay, thank you. Thank you, team. Uh, what I can say is, yeah, coming to drive strength, right? If it is a drive strength, if the CMOS inverter 2WW, that I can say it is a X1. NAND X1 something, that X1 indicates the drive strength, whose widths are PMOS width is 2W, NMOS width is W. For example, X2, then PMOS width is 4W, NMOS width is W. You can ask me, okay, sir, you are increasing, you are going for X2. What's going to happen? That's what we are discussing here. That is called upsizing. Upsizing in the sense we are increasing the drive strength of a particular cell. Okay. Now let's take this delay optimization so that you'll get even more better understanding regarding the drive strength. But coming to the drive strength definition, that is whatever I covered is the uh, definition team. Okay. Now coming to the delay optimization techniques, by upsizing the cell, its drive strength is going to like increase. Hence team, so as widths are going to increase, the resistances are going to reduce, because in our aspect the resistance is
Now,
okay. Okay. So by upsizing, you can increase the, I mean, you can fix the whatever the delay issue, means you can resolve it. You can decrease the delay by inserting the buffers as well. Because team, let us take a net delay, wire delay. It is having the length L. How you can calculate the net delay? It's like one of the standardization is Elmore delay. From that formula, I can say the delay is quadratic function of length, tau directly proportional to L square. So if you reduce the length, there is an enormous reduction in the delay. I can write here, tau is directly proportional to L square. Remember, if you reduce the net length, then the net delay is going to reduce enormously because it's a square, right? Hence, by inserting the buffers, remember the length is going to reduce. Because of that, delay is going to reduce. And even pin swapping as well. We know if there are 6 pins, I mean, there are 6 inputs, the one which is physically far away from the particular design uh, introduce more delay. So yes, pin swapping is also one of the technique to fix the delay. And even logic restructuring. Logic restructuring is simply we are not at all modifying the functionality, but we are we are changing the structure of the design in such a way that it may reduces the delay, but functionality we are not at all disturbing. Similarly, if it are inverter pairs are, I mean, inverter pairs are there, you can remove them. And even cloning or load splitting is also one of the technique. Even VT swapping. Coming to the VT swapping team, in our .lib files, hope you know, we have three types of cells: LVT cells, SVT cells, and HVT cells. Of course, before below 65 nanometer technology, yes, there are a few more are going to add it, but in general, you can take low threshold voltage, standard, and high threshold voltage. Team, remember, whenever threshold voltage is less, delay is going to, delay is going to be less, because it requires very less threshold voltage. At 0.5 volts only, the device is going to become on. So less delay. However, the leakage current, the leakage power is more in this LVT. So do you want to go for fix the delay? Then instead of if suppose is there any cells in HVT mode, then you please make them into LVT cells so that the delay that you can fix, providing that should not go beyond the power value, because when you go with LVT cells, power also increases, remember. Similarly, even area optimization, downsizing, because team, see here, let me write here, this is x1, this is x2 or x31, let's assume. Coming to this team, delay x1 is very high because width is very less now. Similarly, how much area you require? Only width is 2WW only. Area is less only. However, if it is x31 drive strength, then the delay is very less because width is very high. However, as widths are higher, you need to provide room, more space. Hence, the area is more. Of course, team, in our design, we don't use X1 cells or we don't use even X31 as well. Usually from X7 to around. Okay. So according to this, like we choose like in upsizing or downsizing, like your prime concern is area or delay. According to that, we select downsizing or upsizing, even logic restructuring and all. Now, the one more thing, team, power optimization techniques. Power optimization techniques is also one of the important parameter, like VT swapping. VT swapping means here we use HVT cells, because in HVT cells, the time delay is very high, because high threshold voltage, you need to apply some 4 to 5 volts, for example, just for example, whereas the leakage power is very less. Whereas here, the leakage power is very high. Yeah. So VT swapping means meaning here HVT cells. Similarly, downsizing also, logic restructuring, and reducing the switching frequency. Switching frequency in the sense, team, hope you know the dynamic power dissipation formula, CV square F. So here, by reducing the frequency, you can reduce the power, but it doesn't mean that design is encouraging for low frequency operations. No, I told you already, in synthesis, we are meeting timing, area, and power constraints, but preferably timing, remember. And of course, we are adding some clock gating cells to save the dynamic power, and we use some multi VDD techniques and all. So these are the different optimization techniques which are very important, team. Remember, in the even in the course of during the course of work also, you need to concentrate more on the optimization techniques. Okay, this is what, just a second. Is my voice audible? Okay. Then team. Yeah. Now, just a second. I'll clear this canvas. Huh. Right. So as I told you before, there are two types of synthesis: synthesis without DFT, synthesis with DFT. If you ask me, sir, what is Vaishnav, what is a necessity of DFT? See, uh, at the end we need to test, right? So in order to test all the flops whether they are in a correct way or not, for that reason we insert scan chains. That is for sure. However, during this, the net length may increase. Hence, irrespective of their whether they are talking flops or not, they'll reorder the scan chain so that that scan chain length going to reduce. That's what scan chain reordering. It's a separate area where you can have like a good recap on scan chain reordering team. If you ask me, like coming to the scan chain reordering, that you can we can say like this. And now on team, yeah, coming to the reports and all. Yes, outputs, updated SDC, optimized gate level netlist, scan def, do file, log file, and sign off checks. And if you ask me what is this DO file, so as I said, logical equivalence check, functionality check. If it is a cadence environment, we use conformal check. If it is synopsis environment, we use logical equivalence check, like that. And even after completion of synthesis, we go with the LEC, that timing analysis. These two checks we do after synthesis. This is what team. Yeah, just a second. Yes, team. This is what the synthesis design flow, whatever. So this one I have shared with you. And if you have any questions, you can. I'll try to answer. And yeah, the floor is yours, team. You can ask the doubts. Okay, coming to the first question. Can't we move forward if there are violations set up and hold? First of all, team, in synthesis, the clock is ideal. We are assuming the clock is ideal. If the clock is ideal, there are no any hold violations. Remember, hence hold violations, you don't get it, first of all. And coming to the setup violations, if there are setup violations, you need to fix it. You can't move forward. No, delay optimization is very important. So you need to clear the set of violations and then only you need to go. How you can like fix the set of violations is also the point. So coming to the set of violations, so there by increasing the drive strength of the cells, or else the clock to queue delay, like there are techniques which can improve the only setup like which can fix the setup violation. By using them, you need to go. But if you ask me the question, can I go forward? No, but you don't get any hold violation. Now, second question, multi VDD technique. Team, what I can say is in some of the designs, maybe latest or in recent, I can say some of the macros requires a different power supply, another macros requires a different power supply. For that, you need some multi VDD technique, like multi VDD content file, which is a UPF file, where from the powering or whatever particular some set of like macro. What is the supplied power? For remaining macro, what is the power? So to supply the specified power to that particular macro, we use we take the help from the UPF file. That you get more more in detail regarding the multi-UPF file in PNR. Okay, just as a optimization technique, just I have given you in synthesis part. And optimization techniques, whatever you say, sir, this delay optimization, area optimization, and power optimization, whether am I going to do it manually? No, tool will perform. You need to observe, and again you need to resource it. That's it. The tool will take care all these things. Yeah, any other? High fan out net buffering. High fan out net buffering in the sense, can it be considered as cloning, team? Because if any a driver cell contains high fan out, by load splitting or cloning, you can reduce the fan out, right? So it is also one of the delay technique. Delay optimization techniques. Yes, the tool is performing. Yes, that is called cloning only. One of the optimization technique. Okay, then let's conclude the session. Just a second. Yes, team. Actually, that whatever the input delay and taking 2 flops comes under basics of STA. Those are the right people to cover, and definitely when it comes to the when I get the opportunity, sure, I'll take that. Okay, team, then let's conclude. Thanks for your support, team. See you in the next class, and this is Vaishnav signing off. Jai Hind.
Hello, sir.
Thank you, sir. Thank you so much. Thank you, everyone. Thank you, guys. Anyone have any doubt regarding course? Anyone have any doubt regarding course?